we're going to talk about build systems and specifically about Bazel. But first of all, let me just give you a very quick overview of who I work for. We're Zühlke Engineering Limited in the UK. It's a Zühlke Engineering Group, or Zühlke Technology Group, which is a worldwide enterprise these days with about 2,000 employees. Our business model is to transform business. So we do digital consulting, digital experience, software excellence, low-code solutions. We're driving innovation in the cloud, in DevOps, cybersecurity, blockchain, and Internet of Devices, that kind of thing. And we're heavily majoring currently on large language models, machine learning, and AI. That's where the real interest from customers happens to be at the moment. That says, it's also the case that we do much smaller jobs if people want that. If they want, for example, user experience, consultancy, and that kind of thing, we can do that too. So the unique thing about Zühlke is that it's always been engineering-led since its foundation in 1968. And so we've always tried to be at the forefront of technology and also to show what good looks like. And therefore, our customers end up with learning benefits when they take over the solutions by themselves. We're a trusted Microsoft partner. We're also partners with AWS, Google Cloud Provider, and what's the other one?
Excuse me, you mind speaking up a bit?
Okay, yep. Sorry about that. I'll try and raise my voice a little bit. As I said, we're a trusted partner for a number of different companies so we can deliver their solutions. And I've been a software developer since 1980. Also been an agile coach at various times, project manager, project leader, architect, all kinds of stuff. I joined Zühlke Engineering in 2003, in fact, as an architect for mobile architectures. And I've gradually transitioned into various roles. I'm now expert DevOps engineer with experience of things like Terraform, AWS CloudFormation, and so forth. As for the BCS SPA, it was originally started as the Object-Oriented Programming and Systems Specialist Group in about 1985 or 6. I joined about 1987, and I've still got all of the newsletters from issue number 7 to 34 at home, which will shortly be transitioned to the Computing History Museum in Cambridge. I've always been passionate about improving the state of the art in software practice and in technology. Here's our agenda. We're going to have a look at why we need build systems at all, what they are, what their shortcomings are in cases, and novel about Blaze and Bazel and its siblings. And we'll do some exercises, some demonstrations to show you what this stuff looks like, and then come back if there's time to talk about some of the more advanced capabilities. So, ask yourself, what's a build system? Why do we need one? Well, this is brilliantly explained in this book. I found it to be one of the greatest sort of collections of engineering wisdom that it's been my pleasure to read. It shows all about how they think about and go about for engineering in this mega company. They have to build a vast amount of software. I think it's 20 million lines of code on a single source code repository. And that's why they had to start thinking in very basic terms about what the build system does for them. All of this will be recorded, and if anybody wants the slide set, you're very welcome to have it. So, what are the origins of build systems? Well, to begin with, when high-level languages first started making a lot of, reaching a wider audience, you just had a compiler, and you just run the compiler from the command line. You tell it which source files to compile, and spits out an object file. Actually, there's a number of stages to this, and most compilers are in fact miniature build systems by themselves, because they have to do pre-processing, they have to compile the code itself, and they have to locate it in a sort of virtual memory space. They have to link all the pieces together, and eventually there has to be a loader as well that loads it. Sometimes that happens all in one go. These days, most applications are made of pieces that are written in different languages. So you want to use different compilers for different pieces of the system. You want to use code generators. You want to use translators of all kinds of things for specialized domain-specific languages. And you also have specialized tools that churn out documentation, that churn out release notes and this kind of thing. You want to automatically test everything to keep everything at highest possible quality. So we need to run automated unit tests, automated integration tests, and subsystem tests, and system level tests at each stage of the build, including end-to-end tests once you've deployed it. These days, you couldn't build an application from scratch. You need to use various libraries. These can be open source, they can be commercial ones, and in some cases, you get object code only. So we have to treat libraries as dependencies, and thereby hangs a big tail, because you have to obtain them, you have to make them accessible to the builder. And one of the first approaches that was tried for this was to just write shell scripts that will take all of the individual steps, run all the individual tools with the appropriate inputs. But shell scripts have at least one problem, and I'm going to outline that in the next slide. So there's some issues with the scripted builds. First of all, the scripts are very tedious to maintain. Systems inevitably grow in complexity over time, and so debugging the build script becomes a full-time activity. And it's very error prone, because shell scripts were really not designed for debugging and clean code. The performance isn't great, because your script typically can't assume anything about the input files. So it just has to recompile and re-download, in the case of libraries, everything, and run through all the build steps, even if you only change one line of code. And there's very little ways to parallelize those steps. Then there's the problem of magic incantations. So if you've built a typically complex build script, you typically have some command line switches and some options. For example, you'd have an option to do the deployment to production or do the deployment into test environment. And so you have to memorize how you work all those things. And it's disaster prone, because typically you're just running these on individual machines. If you're lucky, you've got an integration server that runs all the build scripts for you. But even if you lose the hard disk on that and you have to replace it, can you be certain that every dependency has been reinstalled on that disk in exactly the right way? And you've all come across this sort of works for me phenomenon, where a build works on one person's machine, but not on the build server, or it works on the build server, but not on half the developers' machines, that kind of stuff. So you're wasting time trying to diagnose those problems. So enter the build system. What's different about build systems is they're declarative. So unlike a standard shell script, build script will specify a series of tasks and define which tasks feed into which other tasks. And so the build system can work out what order to do things in. It's more efficient, because the build system can use timestamps on the files to work out what's changed and what hasn't, so it can know what needs to be rebuilt. And it can also be quite flexible because you can make the build script adaptable to different environments. In C and C++, you have these make scripts, which actually create the build script for you from a shell script, using a number of conventions, which in general, very, very difficult to understand. So what people do is they use an existing make script and adapt it for something new. But in general, that adapts the make file to a different runtime environment, or to use different dependencies depending on an option, what kind of configuration of the product you're trying to build. So I think it's time we did a little exercise. And what I'm going to do is try and run Android Studio here. It'll take a little moment to switch over the display. Or not. Let me see what I can do there. Hopefully this works. Itself. So let's just rearrange things on my screen a little bit. So I'll mirror my display so you can see what I'm seeing. There we go. So here's a tiny little Android manifest. There's a main activity and a little greeter library here. All the greeter does is return a string that says hello Bazel. So the main activity does something logging, and then it says create a greeter and create a click me button. This sort of I don't actually understand Android very well, so I'm not going to go into that in great detail. But what I do want to do is actually run the build. So I think it's working from memory here. Normally I'm able to see that. Okay, so you'll see that it starts a Bazel server. Okay, so it's not main. I'm just going to have to check my my notes. What's it say there? Ah, main app, that's the one. Because yeah, if we look at the manifest, so if that's just the manifest, and then there's a build file here for this particular module, which ties together these source files and says that there's a greeter activity which is going to be used in the app, and then we've got a top level build file which says the name is app. So that's the thing we're building now. Oh dear. Yeah. Thank you for pointing that out. I'm in the top level directory called tutorial. Oh, it's source main, that's what it is. So now this is actually Bazel. in action, and it's downloaded the dependencies, and it's linked the things together and run them. So now I can say Bazel it's mobile, install, start app. So hopefully it'll load that into our emulator over here. Let's make that a bit bigger. And there's the app. So it's displayed the button as defined, and when we click the button, it goes into the main activity, which is displaying the greeting. So that was just a very, very quick demo of what a build system looks like. Probably most of you used something like Maven or Make before. There's Gradle, Nmake, CMake, and lots of others. Rake as well for Ruby. Okay, so I'm going to go back to the presentation now. So the next part of the agenda says, what's wrong with traditional build systems? I'll give you a chance to study this XKCD cartoon. Yeah, builds often take a long time or function in mysterious ways. So here's some fleas that I've come across. So build scripts are a domain-specific language which you have to learn. That costs onboarding time. Code review becomes more onerous, and bugs can accumulate over time, quite subtle ones. The build script works in some cases and not others. The content of the tasks defined in the build script is virtually opaque to the build system. So the build system can't really tell what's going to go on in there, and it can't make many assumptions. So you can make your build task do just about anything because you're basically writing it. You can run a shell script, you can run other commands, and therefore you can defeat the reasonable assumptions that the build system can make. There can be race conditions because some tasks will depend on more than one other task, and depending on which one finishes first, you might have a different result. Tasks, for the same reason that the tasks are opaque, you can't parallelize them easily. So for example, if one task depends on two others, which are not dependent on each other at all, and not dependent on a common source task, they may have side effects. So if they access the same resources, for example, the local dependency cache, then or database records or anything like that, log files, then they can be mutually interfering. And I've actually seen this in a quite recent project where we were using Maven on a Team City build server, which was a farm of build servers. So you took potluck, you get one of 6 when a build runs. And if you're unlucky, another branch of the same source is being built on the same server in parallel. And so what happens is your first part of the Maven build will create some artifacts and put them in the local cache. The second part will consume those artifacts to build something else. And in the meantime, another build has come on a different branch and stuffed something in there which has the same artifact name. And so you get the wrong one. And yeah, build scripts tend to be full of traps for the unwary. You can have unintended dependencies between tasks, in direct ones or indirect ones, dependencies on the environment, and in some cases, task outputs that are deterministic, might depend on the time of day. Again, I've seen these sort of builds that fail between midnight and 1 AM because the build server was running on continental European time and the client was on British time. That type of stuff happens. I've also seen, task A depends on task B, which in turn depends on task C. But at some point, so A has a transitive dependency on C, but at some point somebody's come along and re-engineered B so that it no longer depends on C. So when you're running A, you're really puzzled as to why your dependencies are no longer there. Also, the incremental building can be ineffective because, again, build systems have to err on the side of caution and make few assumptions about tasks. So in general, they tend to rerun them if they can't be absolutely certain that none of the inputs have changed. And the Java compilation tends to be the big bugbear in this. When you run a Maven build step, if any one of the files has changed in a module, it'll recompile the lot, including your test files. So it takes longer than it needs to. And then, of course, having compiled them, it has to run all the tests again. Biggest bugbear of all is dependency management. And we'll come and talk about dependency management in more detail a bit later. But dependencies can be on other tasks. They can be on artifacts that come from your own code base. They can be on artifacts from another team. They can be on a tool, either made by your own team or another team. They can be on data. Sometimes, you need fast ranging test data to run something. And you can be dependent on external artifacts such as a library, a tool, or indeed external data. I've seen tests that depend on stuff made available on the Google Big Data service, big table service, such as weather data. And normally it conforms to a certain pattern, but in some cases, something isn't there that you expect to be there, and the test fails. And there's more. So what Google developed was something called Blaze, which is their in-house build system. And it took, I think since about 2004, 5, something like that, is when they started working on it. In 2014, it was open sourced and they renamed it Bazel, which is just an anagram of Blaze. But Bazel or Bazel is now open source and anybody can use it. So what did they do? They had to basically go back to fundamental principles. And they realized that these build systems that were in common use give far too much power to individual engineers by letting anybody create a new task. So what they did instead was to define a small number of configurable tasks, which are called actions, and have parameters. So obviously your most important task is building some code. So the engineers simply tell the system what they want built, but not how to build it, and the system decides. And the build files in Bazel are declarative manifests. So rather than defining tasks, they define artifacts. And that's the crucial differences. So for each artifact, it defines the dependencies and some options which govern how the artifact is built. So you run Bazel on the command line, as you've seen already, by just naming what you want built. And Bazel then configures and runs and schedules all of the compilation steps, using all the required tools. I should say, though, that Bazel does provide the ability to define custom rules, because not every possible tool is catered for. So you can author your own tools, or you can look on GitHub or elsewhere for other tools that have been added to Bazel over the time, and even the appropriate permissions within the build system, you can bring those in. There's a quote here from one of the people writing in that book I showed you. Because the build system now has full control over what tools are being run when, it can make stronger guarantees that allow it to be far more efficient while still guaranteeing correctness. And that's the crucial thing. It used to be you had to trade off correctness against speed, but with Bazel you can have both. There's an analogy here with functional programming languages. If you're familiar with imperative programming languages such as C, Java, Python, and Go, they consist of a series of statements to be executed one after the other, together with some control flow statements like branches and function calls and loops. And task-based build systems are essentially very much like that. You find a series of build steps, and the task dependencies effectively govern the control flow. But if you're familiar with functional programming language such as ML, Haskell, F#, your application is structured more like a system of mathematical equations or functions. And so you describe the computation that has to be performed in abstract form, in abstract terms, and then ultimately you feed in some parameters and it goes through the system and obviously answer at the end. The compiler decides how to apply these functions to the inputs and how to string them together to generate the end result. That maps to the notion of an artifact-based build manifest, where the system works out exactly how to achieve the result you asked for. There are a lot of problems, of course, which don't really lend themselves to functional languages. However, if you can do it, great advantages will arise. The compiler can easily parallelize the operations and the computations. It can make strong guarantees about correctness of the outcome. And in fact, we find that the easiest such problems are those that transform data from one form into another form. And applying rules. That's exactly what a build system is doing. It's taking a bunch of source files and transforming them. Source files and external dependencies and transforming them into something else. So that's why it looks promising. And over time, these are the set of concepts that have crystallized out. So first of all, you have a target. A target is an artifact. And you use one of the predefined tasks, such as Java binary or Java library, to generate the target with configuration arguments that tell it, for example, compiler switches, language level, the source files to use, and so forth. For each target, you have a name argument. That's got to be there, because otherwise you don't have any way of referencing that artifact from anywhere else. So other targets and on the command line, you need to be able to specify either the artifact label, which is its full path name. You saw me writing earlier, //source/main, path, and then colon app, and that's its name, the last bit. Then you have to specify its sources, but you don't always have to. It depends on what sort of target, what sort of action we're defining. But if it has a sources argument, it identifies the source files that have to be compiled to the target artifact. And these source files may be ultimately source files, or they may be files produced by another action that generates artifacts. We don't really care at that stage. We can also define dependencies. These might be artifacts, either within the workspace or external to the workspace, which need to be linked in. So the build system works out which ones have to be built and which ones it can just obtain from somewhere else. And because we can also create dependencies on tool chains, we can specify exactly which tools are going to be used to do things like compilation and linking. Anybody who's used, for example, what's that called, MINGW, that sort of a tool chain will know that it incorporates a whole range of tools that have been designed to work together. And regardless of the environment in which you're executing the tool chain, it produces an identical result. interesting concept of visibility for each artifact, and indeed each package. I'll come on to that next. You can specify its visibility. There's a default visibility for the package, which is defined at the top of the package, and that says if you don't specify visibility, this is the visibility you get for an artifact, but you can override that, which makes it easy to kind of limit the namespace pollution, if you like, by intermediate artifacts that you don't want anybody outside this particular module to see. There's some additional concepts. I just mentioned module or repository. So it's slightly confusing. Bazel refers to a subtree of the source hierarchy as a repository. Recently, they've started using more the term module, because that's more kind of our understanding of how modules work. So yeah, you can specify a workspace as a that's the legacy term. Nowadays, you tend to use module of Bazel, and in fact, you possibly saw that when I ran the build earlier, it created a module Bazel for me, because it said, "Oh, we haven't got one," so it creates it, and you can add it to the source code. And then there can be rules within the module file that specify any external repos that are also used. So the workspace is really the main repository, and you run all the Bazel commands from the main repository, which tends to be, but doesn't have to be, at the top of the module hierarchy. And any external repos that are used have to be defined in rules. They're called repository rules. Package, very much like Java packages. So within the repo, you're decomposed into a package hierarchy, which maps onto the file system hierarchy. The only way to tell whether something is the root of a package is if it's got a build file in it. And the build file, which is written in a language called Starlark, that defines all the targets of that package. So you can have three types of targets: files, which are source files or generated files, and these are artifacts. And then you can also have rules which define how to transform one type of target into another type. And finally, package groups. I'll talk about those. A package group is a group of packages, as the name implies, and you can nest them. So you can have packages as well as other package groups within a package group. And again, you can specify the accessibility or visibility of each of these packages within the group for consumption by any other artifact. So a package group can only be referenced from the visibility attribute of another rule or package. Okay, I think we're ready for some more demonstrations. And I hope this time this will work. What I'm going to try and do is keep my notes open at the same time as showing you the application. So I'm going to use IntelliJ IDEA for this and move that to the other workspace, the other window. Right, everybody seeing that? Okay, great. So this comes straight from the tutorial examples that provided with Bazel. And if you'd like to follow along, you can open the Bazel build start page and run the examples along with me. So we're in the first of the tutorials, stage one. What this is designed to demonstrate is how you can gradually refactor an application to make it more efficient to build. So to show the structure of the code, we have a hello world CC, which you can see on the screen. And main function here, which just says who is world, but you can override that on the command line by giving it a different name to greet. And then it just sends to the standard out a string which is produced by get greet with that name. And then it also prints the local type. So we've got two functions here, get greet. One concatenates the word hello with the name, and the other one changes the current time and converts it to a string that it can output to the standard output. Okay, and then we've created a build file in main, which loads from this dependency here, loads the CC binary activity or action. And then we use CC binary and gives it a name. This is the name of the artifact that's going to produce. And the sources are hello world CC, just the one file. In the workspace file, there's rather more. Most of this could probably go in the module.bazel file, but I didn't want to change too much from the tutorial example. It's quite old. So this is saying from Bazel tools build blah 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 .bcl load HTTP archive and then invoke it. So what's this doing? This is using the aspect GCC tool chain. Various parameters that we don't need to go into here, but the main thing is that it's using this URL to obtain the tool chain as a dependency. We load something else from repositories. So we go to the GCC toolchain dependencies because the toolchain itself has dependencies. And then we invoke that so that it obtains the things it needs. And finally, we're loading from toolchain defs, GCC register toolchain, which is another activity, and something else called architectures, or arcs for short. So we're registering this toolchain now, having loaded the task, and giving this name GCC toolchain x86-64, which you notice was, you get that, the target architecture. So having got that, it should run the build. Let's see whether it does. So, Bazel, main, that's the path. It's just under main there. And then we say the name we want to run is hello world, which is the name of the artifact in the build file. This may take some time because I haven't run this for a bit. So what tends to happen is that Bazel maintains a local cache of all kinds of dependencies, but it does periodically check whether they're still up to date. So let's just run it very quickly. I think after about a week, things time out. So having run it, we can run it again, and it should complete instantly. There's nothing more to do. Nothing's changed. I can now run this binary. You'll see that it's produced these symlinks. It's created a temporary directory under my /temp of the hierarchy, and these are folders within it. And the reason it's using symlinks for that is so that every action is isolated from the other. So every other action, even though the symbolic links seem to point to the same place. let's run this. So it's Bazel bin. It's difficult for me to type and look behind me. Slash. Hello world. So that it's just created a binary within that structure, which, as you can see, says hello world and today's date and time. If I say hello world, I've tried this by the way. So can I say hello, Olivia? Yes, it does. Okay. Now, the next step is to go to, we're going to say, well, that's quite a monolithic sort of program, isn't it? So we'd like to factor out the getGreet function into a library. So that we can see in stage 2. So we've got an greet.h, which defines the interface to that function, and we've got the same function as before. Hello world.cc is simplified because it's now only got the main and the print local type on it, but it's using greet.h to call that function. And what does our build file look like? And you see it's now loading 2 rules, the CC binary and the CC library. So it's creating a CC library from hellogreet.cc, and the parameters are hellogreet, which is the name, and hellogreet.cc is the input, the source file, and it also defines a header file. So these are the things that need to be combined to make a CC library. And then the binary, as before, is hello world, but it's only got 1 source now instead of 2, and instead it's got a dependency, which is hello greet, and you can see that it's using just the artifact name with no path because it's in the same place, so it doesn't need to redirect to it. So if we build this, let's go back to the list. So we'll build main hello world again, which is in that build file. We've already done it. It's really quick.
It's still in stage 1.
Sorry?
It's still in stage 1.
Oh, well, that's because we ran before. Thank you for pointing that out. Let's do it again. Because it hasn't built it for quite a while. So it's rebuilding everything. This can take a while, and depends on how fast the network is. Well, at the moment, it's fetching a tool chain, which is quite long. SDK information first code. This is the Mac. Hang on. You can see the difference when you first run this after a week or so, or the very first time you run it. It take a while to set themselves up. The way that it was designed is it's guaranteed to produce the same build environment and finally run the computer. What I haven't tested out is what you have to do if you're developing on a Mac, for example, and the build server is a Linux machine. I expect you might have to Apply a slightly different tool chain for that. Based on the environment. Okay, so here we are. Built, and if we run it again, very quick. If we run the actual application, of course, it hasn't changed at all because it was simply a refactoring. We haven't changed anything. If I now change something trivial, such as hello, let's change the LLCC. So make that a capital W.
That might be the stage 1 file.
Big one.
Yeah.
Oh, so that is well spotted. That would have been embarrassing, wouldn't it? Stage 2 hello world CC. So we'll make that capital W, so it's modified just one file. There we go. And then rerun the build. It should build. It should compile only the one file. I don't know if you can see that. Let's see if we can make it a bit bigger. Oh, didn't rebuild. There. So it says it's only found one target to compile. The hello world at the top didn't rebuild the library. Okay. No. Right. Sorry, I'm
Just drag it.
double click it. So if we go to stage 3. The idea now is that we actually create a library folder, which can, so this is like emulating an external dependency. So we're going to move the hello times, the code from the print local time into there. Close all of these to avoid any further confusion. So now, hello world CC becomes even simpler because it's only got the main function in it. It says we're going to call hello time and hello greet for these other functions like print local time and get greet. Get greet I don't think has changed. That's still a library. But this is going to be an external dependency. So in build, our CC binary now says a second dependency, which is hello time from the lib package. And you can see that this package has another build file in it. It just creates this library called hello time. And you can see that it says its visibility will be to anything in the package called main, so that we can use it. In here, we just looked at that, didn't we? And the workspace file hasn't changed either. So let's build this one. So this time it's going to have to, again, download all the dependencies and so forth, because it's actually, we haven't modified anything, we just moved to a different directory. It's going to take a little while. Is everybody clear about how this library package is different from the main package? So it's external library dependency, and these library dependencies can come from other builds, from public repositories and that kind of thing. One of the things that they do at Google is basically to try and reduce the number of dependencies by making everything part of the source code. This is why there's a huge monorepo there. So that's completed. And if we run this again, it still works the same way. But if I leave out that extra parameter, I think how that works with small w again because we moved to a different folder where the source code isn't there. Right. So I'd like to just briefly, because I think we have time, go through a Java tutorial. Just to show you what that looks like. This is structured very much like a Maven repository, source main Java, source test Java, and so forth, and resources. And below. Particular case, we'll see that the workspace file is completely empty. It doesn't mean anything. Declare every.
Sorry, why is the workspace file empty for the Java file? What was the Java project?
Sorry, I didn't catch the question.
Why is the workspace file empty for the Java project?
I honestly have to tell you, I don't really know. There's a need for a workspace file to define a repo. In the case of C and C++, we had to define a number of things to be loaded. Those could have gone in the module.bzl file, but for this tutorial, it's too old. It hadn't done that. I think it's easier for the tool to do Java compilations, and therefore it didn't need to load so many prerequisites. So we didn't have to do that. So at this top level, you've got a build which loads Java binary, and it creates something called project runner. And it says all the source files are in source main Java.com example. So that's here. It's going to ignore what's in command line. So we've just got a greeting.java and a project runner. And the name of the binary that's going to produce is also project runner. You notice there's no further build files or anything like that. It's all done at one level. So we need to move to that. So if we then yeah, Bazel build, and the path is just to the top level. We'll call it project runner. I'm honestly a bit confused now because project runner is way down there, but somehow the build still seems to find it. Maybe because it's that glob. Of course, yes. We're saying the binary is defined at this level, project runner. We don't need to specify the whole part down. It's all handled by the glob. So now it's fetching a tool chain. It's ignoring the JDK that's installed on my machine and building using the Zulu 11 JDK. What are we up to now? Java 23. So these examples are a little bit old. And of course, it also continues to work. Oh, it's also downloading the 21 JDK. I'm not sure why it needs both.
You didn't define which Java version should be run, though. Did you? Or
I haven't. That's nowhere in this. I mean, you can, but I think it just uses defaults. Right. So it's built, and to run it, we just have to use the Bazel build. Sorry, Bazel bin project runner. And it says hi. Now the thing is, if we say file that, you'll see it's a shell script because it's created a jar file and needs a shell script to invoke it. So this isn't ideal for deployment to any sort of real runtime environment. So what can we do next? Well, I've been through the exercise and we've got some things in the shelf. So there's a build file there, which is a little bit complicated if you just have a look at it. It's saying we're going to now build Project Runner with a different glob. So it's just going to use Project Runner.java and specify this main class. And it has a dependency on something called greeter. So this is the same sort of things before. We're creating a Java library called greeter with a different source. So if I unshelve this, we run this again. So again, it's building Project Runner. And again, it's creating us a run script for it. The next stage, we want to make a change to a file. So if we make a change to project runner.java, which is well, the easy thing is just to put comment. I don't accept that. No, doesn't matter. It's just a trivial change to the file. And it's already been auto-saved. So if I build it again, you should see that it's only building Project Runner and creating the jar file again. Now, there's a top-level build file. Which has a package default visibility, you see. It says it's public, so anybody can reference it. If we take that away, then this Java library will have a default visibility of private. So let's see what happens then. So now it's saying there's no such target. It's not declared. And why is that? Oh, syntax error.
Probably it's because of the build file rather than the .java file.
Well, that's how you do a Java, isn't it?
Yeah, but on the build file, we are not sure. Like,
the actual error itself is on the build file.
yeah, it's right there on line 2 or something. You need to delete that one.
Oh, yes. This is not the way to comment, is it?
Yeah.
What I have to do is
Hash.
that. Okay. Thank you. We've got more syntax. So let's build it again. So that worked, and it worked out. I have to change this file because I've changed to it, but that's all. Now, if we go to the next, yeah, so we're going to try and build, instead of using this project runner, we're going to use the command line package. So that's got a runner.java in it, and it's got a build, which says we're going to create something not called project runner, but runner. And the source will be runner.java. And this is a library, which depends on greeter. Well, what's greeter? Well, that's going to be defined. That's our greeter, but where's the actual build file for the greeter? Ah, there it is. Okay, so this is saying we're going to depend within this module here, within this package, sorry, on this library generated at the top level. So let's try doing that. Say Bazel build. And this time I'm going to actually give it the full path. So it's /source /main /com /example /cmd line. Spell that correctly. And the name is going to be runner. Right, so that didn't work because greeter is not visible from the target. So we're trying to build runner, and it's got a dependency on greeter, but it can't see that. So we need to make greeter visible. So I'm just going to copy that from here. It seems I can't copy that, so I'm just going to have to type it. So the Java library needs a visibility statement. And the way you do that is to type visibility equals, and then this is where you normally use a list of visibilities. So we want to make it visible to the package that's going to consume it, which is source main of our com example cmd line colon, and then we want to say everything in that package. An alternative would be to say subpackages, or very specifically target within that package. So let's see what that's going to look. Yay! So to run it, we'll type Bazel bin. What's name? Java. To produce the whole path that the artifact has in it. Example, command line, runner. And it says hi. Great. So we've still got a build script there, a sort of run script there. But what we can do, this little trick that Bazel has, is when we do the build, we can say deploy.jar. And then it'll create a jar file with all the dependencies bundled in. So that's if I jar TF that. See, it contains common example, command line, the runner class, the greeting class. So everything's been built in together. And to run it, let's say Java minus jar, that thing, and it runs.
I just have one question.
Yes.
So the build file location, to be fair enough, it has no significance in this case. So let's say if you have another folder, and you save like X folder, and then you save a build, but the build folder location, I mean, the dependencies that it has, it is also on the other side, or it is on some different file path. So basically, the build file location has no significance in this case, right?
That's right. So that's where we use the external repo type of thing. We use a repo rule. You can gain access to that repo, and then you just specify the path. You notice that some of these dependencies have got an @ sign in front of them. So that's like a locally external repo. If you double @ then it goes off to the internet.
Okay. No, thanks.
So I think it's time to return to the. Let me just have a check how the food's doing. It's a tracker. It's out for delivery, so shouldn't be long now. Yeah. So we've done that. Some quick tricks that we want to say. Bazel has a nice query language. You know, in Maven, you can do a Maven dependency tree type of thing to show you all the dependencies. Well, this has got equivalent. You can learn about the code base by running various command line queries, which analyze the build files within a workspace. So in order to do precisely that, what you do is Bazel query --, no implicit dips, so that's the implicit dependencies, and then the dependencies of target. Ignore the bit in grey for the moment. So if we do that for our project runner, that looks at an example, and it shows you that it's got these dependencies, 4 artifacts, 1 language, and a tool chain. But it's not very easy to see how that's structured. So if you add the bit in grey and you say output graph, and then pass that through something called dot, which is a nice little local tool, in format PNG, then you can create a PNG graph file, and that looks like this. So it's much more obvious, what's relying on what. So we had our greeter library, which had the greeting.java as its dependency. And we had the project runner.java, which was direct dependency of project runner. And then it was also dependent on the tools tool chain. It's got something called sandboxing, and this is really important for allowing parallelization without ill effects. So every action is isolated from every other action via the system sandbox. And so each action will see the inputs that have been declared for it and all the outputs that it produces in the course of running. But any outputs that haven't been declared as outputs will be discarded when this action completes. And if you run several of these actions in parallel, they're completely isolated from each other. They can't even communicate via the network. So that's why these symlinks appear inside the file hierarchy, because that allows file system sandbox. It's very similar to Docker sandbox. to isolate these inputs and outputs from each other. We talked earlier about dependency management, and the really big problem is this one. If you have an artifact that depends on something called dependency A at version A, which in turn depends on dependency version X of Z, and dependency B, which also depends on version on Z, but a different version, you've got a clash. The ways to resolve these would be to change the version number of A and or B until you've got something compatible. But quite often it's dependency hell, because you've then got other things which are knocked out of kilter by this. So what are the ways we can manage with this? Well, one is that you keep everything static. Once you've adjusted things to the point where it works, you keep everything static. But the gotcha is if you find a security vulnerability in any of those dependencies, then you're forced to upgrade and you're back in dependency hell. There is this widespread concept of semantic versioning, where you've got a major, a minor version, and a patch version. And the assumption is that the producer of the artifact or the dependency knows, what level of dependency you've got on it. So whether you need to upgrade the patch version, the minor version, or the major version tends to be breaking changes. And you quite often see libraries which are being maintained at 2.x as well as 3.y in parallel, because this is the problem. There is the bundled distribution model, and you've all come across Linux distributions where somebody takes the trouble of integrating everything together at a version. Spring is a great one because it brings in dependencies of just about everything else. So a particular version of Spring is a harmonized version of everything that it relies upon. But then, of course, you're reliant on another third party. And there's this live at head model, which they're trying to introduce, or some people are trying to introduce. So you always use the latest of everything. And because you're building everything, every time anything changes, you should be able to catch whenever there's an incompatibility through your unit tests. However, it's unproven. They haven't shown that it's sufficiently efficient to be able to do it. And it may be a lot of work to actually keep all the tests green all of the time, because as soon as something goes wrong, you have to leap on it and do something. Remember that dependencies are contracts between providers and consumers, with both having some rights and some responsibilities. So it's not free to add a dependency to a project. You might understand what the library is, but it gives you something, but it costs you something as well. And providing a dependency to other teams isn't free either, because you can't throw it over the wall. If you just don't maintain it, then compatibility challenges will result, and they may find that there's a problem with your dependency and they can't upgrade. There's nothing more. If you give stability guarantees, such as through semantic versioning, that limits your choices in terms of architecture and future changes. So it epitomizes internal usage. And a lack of stability guarantees is not good either, because it runs foul of something called Hiram's law, which is the observation that with a sufficient number of users of an API, it doesn't matter what you promise in the contract, any and all observable behaviors of your system will be depended on by somebody. And that's Hiram was one of the authors of that Google engineering book. This is a lovely illustration of what can happen. Breaking change that you didn't expect, breaking anybody. I love XKCD. So, as I said before, the takeaway is if you can turn a dependency problem into a source code control problem, then you've basically hacked it. Semantic versioning is unreliable because it can either lead to overdependency or inadequate compatibility guarantees. Certainly the idea that you can specify a sort of range of versions that are compatible is not conducive to producing reproducible results from builds. A real proof of the pudding is in your CI/CD pipeline. And one strategy that they've successfully, I think, pioneered at Google and shown that it works is that if you must upgrade something in order to generate compatibility between transitive dependencies, use the minimum version update that you can. Because every time you upgrade more than that, you're going to break something else. So external dependencies have to be deterministic. So you use a cache like Artifactory, which makes you slightly independent of network interruptions or server problems. But here are the things: security. You've come across supply chain attacks such as the Wind River, I think it was, one a couple of years ago. They're becoming more common. And so your artifact could be replaced with a dependency that has something malicious in it. The thing that I heard about today was a new idea, was artificial intelligence. A lot of these artificial intelligence generative AIs can tell you about some library or some product or some tool, which doesn't really exist. And then somebody else finds that and actually squats on that thing, supplies a fake library or whatever that has the name mentioned in the GPT output, and they can insinuate a fake dependency on you in that way. Yes, this is the other thing, that if you rerun a build, it has to be from any commit in history, it has to have the same results. So you need the previous set of dependencies to be produced as well. And typically you don't want to download all dependencies every time, so you have a local cache, but you can't constantly keep going to check whether the files are fresh, up to date. And you want traceability. So if any change happens in your dependencies, you need to be able to point that to a commit. So it needs to have a matching source code change. So how have they fixed that? Well, they've used this manifest file. You might have seen it in the examples. It created a module.lock file, which is very similar to the kind of npm, what are they called? Package lock files. And what it does, it has a cryptographic hash of every external dependency. So not just the version number, but an actual verification check. And this hash has two purposes. So the first is that you don't need to refresh local cache dependencies if the hash that you get from the dependency service matches the one that's in your cache, in your local lock file. But also if it has changed, yeah, if it doesn't match the hash, then you download the new version of the dependency and update the log file, which is then submitted into your source code repository. So you've always got a traceable change. If it's on the build pipeline, obviously you can't check things back in, so you configure it to fail the build if the changes don't match. And that's how it guarantees reproducibility. Very quickly, a couple more things: distributed builds. So your typical sort of environment with a workstation, another workstation, a build server, all connected by a network. And we add this shared artifact cache rather than having a cache on every single machine. And what this could be a Redis cache, and Nginx or Bazel provides its own called Bazel Remote, or it could be cloud storage if you're building in the cloud. So whenever you need an artifact, it first checks whether that's already in the shared cache, and if so, it grabs it from there. Otherwise, it builds the artifact that's needed and then uploads it to the cache. So the next person building might need to do so again. So each artifact in the cache is keyed on both its target and a hash of its inputs, so that you be sure that it's built from the same sources. And then building upon that, we have this idea of distributed builds. So again, we've got that developer setup, but now we've got also a build master file. So rather than, you noticed that I was running a local server by default, we can configure Bazel to use the build master instead and actually farm out all of the build steps to that. So you send your build command to the build master, and it decides how to split it up amongst the farm of worker machines. And of course, the workers share the artifacts using the shared cache that we had before, and the end result is another artifact in the shared cache, which the requester can then retrieve. So that's how you parallelize builds natively. Again, there's a number of solutions available. Bazel provides its own called Build Farm. There's Build Barn and Build Grid, Native Link, and then there's commercial products as well, because various vendors have seen this as an opportunity to really supercharge build. So that's it basically. Are there questions? There's a lot more that I could say, but we've run out of time. And I've run out of ideas. Well, I suggest we have a look to see whether the pizza's here. Oh, I think it is. Would you like to have a look? Right, it says. So I suggest we adjourn. I'll stop the recording now.